Alrighty, howdy folks. So let's get back to part 2 in chapter 12, section 5. So this is about planes, planes in 3 dimensions. Okay, alright, so let's say we have an XYZ coordinate system like this, and to find the equation of a plane, here is the idea. What all do we have? Okay, let's say we have a plane that looks like that. It's that plane is in space. The, the plane is in space is a fancy way of simply saying something that is in 3 dimensions. You know. Okay. Um, one caveat here is notice how I drew it as sort of rectangular, right? But when we actually say plane, just like when we say line, we may show an itty-bitty portion of a line, but we actually mean that line extends all the way to infinity on each side. In the same way, this plane extends all the way to infinity. Okay? Only for convenient drawing purposes, we show a piece of it. In fact, in this case, sort of rectangular-ish piece. What else do we know about this one? So let's look at the different aspects of it. So that's the plane, and we know a point on the plane, and that P0 happens to be a point on the plane. And like before with the lines, R sub 0 represents the position vector of that point. What is a position vector? Again, a vector that starts at the origin and extends towards wherever that point is. The position vector of a position, that is a point. A point is positioned at a certain place, certain XYZ, and we're doing that. Okay. And what's with this N that is sticking out, and what's up with that right angle thing? That is to show that this N is the normal vector to the plane. What is it? The N is a normal vector to the plane. What in the world is a normal vector to the plane? The best way I can explain that is, uh, do you have a flat table on which you're sitting? Well, uh, to the flat surface of the table, now uh, take a pencil and put it perpendicular to that flat top of a table. That pencil is perpendicular to this flat plane top. That pencil sort of represents the normal vector to the plane. So a plane is, how should I say, just flat, and perpendicular to that flat, there is a line or a vector. That vector is the normal vector. Now, when you have curved surfaces, then it's going to get a bit tricky. Normal is pointing in which direction and all that we have to talk about. But at least when we're talking about simple planes, normal vector is fairly clear, right? Good. So those are a couple of things on this one. What else? Our objective is to do what? Our objective is to find the equation of a plane. What do we mean by find equation of a plane? Please pay attention to this. When we say find an equation to the plane, we mean find a way of representing every point on the plane. Okay? Finding an equation of the plane means finding the XYZ coordinates, or alternatively, a vector to that XYZ, a position vector, of every point on the plane. Okay? So, with that, check this out. I picked some arbitrary point P, and a position vector of it is R. So this R is going from the origin to a point, some arbitrary point on the plane. Okay, now our objective is to find that one, right? Check this out. Can I immediately do R minus R sub 0? If this is R, would you agree this is R minus R sub 0? Even if you don't, maybe what you're more familiar with is, would you say R sub 0 plus some vector is equal to R, this vector? So if R sub 0, let's call it A, R sub 0 plus A equals R, then R equals, by simple algebra, R must be R minus R sub 0, or that A must be R minus R sub 0, right? That's all I'm trying to say. So this vector is R minus R sub 0. Okay, what does that got to do with any of this? See, we need all this background so that we can say if P sub 0, people call it P naught is has coordinates x naught, y naught, z naught, is a point on the plane with R sub 0 being its position vector, and n is has the components a, b, c is perpendicular to the plane, that's a normal vector, then we find the equation of that plane. How? Let P be an arbitrary point and R be its position vector. Since the vector R minus R sub 0 lies on the plane, is it true that the vector R minus R sub 0 lies on the plane? Think about it. Can you convince yourself that the vector R minus R sub 0 lies on the plane? Yes, it must, because does P sub 0 lie on the plane? Yup. Does P lie on the plane? Yup. So a vector going from one point on the plane to another point on the plane, shouldn't that vector lie on the plane? That's the argument. Yeah. So since the vector are on the plane, and since n is perpendicular to the plane, these two vectors must be orthogonal. What is orthogonal? Yeah, simply they are perpendicular to each other. Oh, okay. So what should happen? We got this vector and that vector, the r minus r 0 vector and the n vector are perpendicular. So the dot product must be 0. And that is what gives us the equation n dot r minus r sub 0 equals 0. Cool. And that implies we can rewrite this as n dot r minus n dot r sub 0 is equal to 0, which is the same as n dot r equals n dot r sub 0. That's how we find the equation. That's the vector equation. What else can we do? Let's see. Is n just ABC has components ABC? That's what we said here. N has components ABC. And r minus r sub 0, right, is this guy, is the vector from P sub 0 to P. So if we do a head minus tail, we get x minus x sub 0 as the x component, y minus y 0 as the y component, and z minus 0. So we are taking the dot product of these two things and setting that equal to 0 based on the vector equation. Okay. Now do you remember what the dot product of these two vectors is? Take A and multiply by x minus x sub 0 plus b times y minus y sub 0, and right, plus c times z minus 0. So that's equal to 0. Okay, can we go further? That's the scalar equation, and we can go further and write this as ax plus by plus cz plus d equal to 0. What? Yeah, check this out. Do I get ax from here? A times x? Yep, that's what I wrote. By? Yep, that's cz. Yeah, but what happened to that ax 0, man? Minus ax 0 minus by 0 minus cz sub 0. Well, a is a constant. X sub 0 is a known point, so it's a constant. So a x sub 0, just multiply out. A is not a known quantity. Take it back. A times x sub 0. All of them, those things, add them up and call it a single d. Right? So the d is nothing but minus ax0 minus by0 minus cz0. Okay, and so that's the linear equation. Okay, What else? So, yeah, let's. Whoa, whoa, whoa. I was about to just move on. Oh, no, no, no. Here, we need to stop at this point. This equation is very, very important. So, the equation of the plane, the linear equation, is ax plus by plus cz plus d is equal to 0. Okay, uh, a, b, c, what are they? They are the components of the normal vector. Keep that in mind. A, B, C are the components of the normal vector. So the only thing is, what's with this D? Let me see if I have written anything. Note that ABC is the components of the normal vector. Then I said, as we change the value of D, we get a different parallel plane. When D is 0, this AX plus BY plus CZ is equal to 0. This is one plane. However, if D is 1, we get another plane which is parallel to this original plane. The x plus by plus c is equal to 0. If we were to call that as the original plane, you add a d to that thing, that scoots the plane up if d is positive, and so on. So you keep getting different parallel planes by changing the value of d. However, this is one of the most what should I say, popular equations to use for a plane. Ax plus by plus cz plus d equal to 0. Okay. What else? Angle between two planes. This is another one. Now check this out. Um, let's say we have two planes that that intersect. They are infinity stretching infinitely. Because each one is a plane, we can draw a normal vector to each of them. Let's say the normal vector to the first plane is n1 and the normal vector to the second plane is n2. Our objective is to find the angle between the planes. Hmm. Is the angle between the planes related to the angle between the normal vectors of the plane? You bet. Okay. So we can, if the equations of the two planes are a1 equals b1 plus b1y plus c1z plus d1 equals 0 and a2x plus b2y plus c2z, the angle between those two planes, note that the angle between the planes is the same as the angle between the normal vectors of those two planes. So to find the angle between two planes is not so straightforward. However, the moment we talk about the normal vectors to those planes, finding the angle between two vectors is piece of cake. Why? Well, you remember that the dot product a dot b is equal to vector a dot vector b is nothing but magnitude of a times magnitude of b times cosine theta. So if we know two vectors n1 and n2, and we take the dot product of those two things and divide by the magnitude of n1 times magnitude of n2, we get cosine theta. And from that you can figure out the angle between the two planes. Cool? So that's the next concept. And yeah, that's exactly what I did here. All right. So probably there's no need to memorize this A1, A2 plus B1, B2 and all that nonsense. N1 is A1, B1, C1, dude. A2, B2, N2 is A2, B2, C2. Well, can you take the dot product of the two and divide them by the product of the magnitudes? Piece of cake. That's all there is to it. Okay. All right. Next, find the equation of the there are quite a few problems, and I really would like you to pay attention to all these problems. So I told you this section is one that is kind of important and just a tad tricky. Find the equation of the plane. The plane through the point this with normal vector 2i plus j minus k, right? You know a point on the plane and the normal vector of the plane. Going back, is that stuff important? What do we do? Oh, ax plus by plus cz plus d equals 0. What are ABC? ABC are the components of the XYZ components of the normal vector. Okay, D is the constant that tells you where the plane is located. Okay, so recall that the equation of a plane is AX plus B plus ABC are the components of the normal vector. So at least that part, AX plus BY plus CZ part, seems to be obvious based on ABC being, you tell me, A, B, C, what are they in this case? Well, the x component of the normal vector is 2, y component is 1, and z component is negative 1. So 2, 1, negative 1 are A, B, C. Would you agree? So here we have A equals 2, B equals 1, C equals negative 1. Yep. And so plugging these, we get for A, B, and C, we get 2x plus y minus z plus d. And d is still unknown. Would you agree? A, B, C we know based on the normal vector. And 2x plus y plus z minus z plus d is what we get, equal to 0. Any idea how to find d? Well, we know a point on the plane, right? 5, 3, and 5 are its coordinates. What can it do? What can we do with that information? Simple. Take x equals 5, y equals 3, and z equals 5 and plug into this equation. And everything would be known, and d is the only thing that we wouldn't know, and we can solve for d, right? Since 5, 3, 5 is a point on the plane, we plug x equals 5, and to get 2 times 5 plus d and solve for d, d happens to be negative 8. Done. Just plug all of this. The equation of the plane is 2x plus y minus z minus 8 equals 0. I plugged in all the known quantities. That's all there is to it. This problem is certainly fairly straightforward. Would you agree? All right, let's move on to the next one. Find the equation of the plane through the point 3, negative 2, and 8. Okay, so we know a point on the plane, and it's got to be parallel to that plane z equals x plus y. Our plane must be parallel to this plane, apparently. Okay, any thoughts on how to approach this problem? Is it good that we're given at least one point on the plane? Yep, that'll come in handy to figure out d. We need a normal vector. Is there any information given about the normal vector of our plane? That's the, what's that American expression? That's the $64,000 question. I don't know why it has to be 64,000. That never made sense to me. But I think I heard some other numbers too. That's a $1,000,000 question. Okay, whatever. Any thoughts on how to find the normal vector to our plane? Duh. If our plane is parallel to this plane, our plane is parallel to this z equals x plus y plane, then they both must have the same normal vector, right? The normal vector to one is normal to the other plane as well, because the planes themselves are parallel to each other. That's the key to solving this problem. Okay, so let's look at this. Parallel to the plane, and we say where ABC, normal vector, blah. Yeah. Since our plane and the given plane are parallel, the normal vector of one is also the normal vector of the other. And so, the normal vector of this parallel plane is 1, 1, negative 1? Where did I get that from? I'll simply write this as x plus y minus z equals 0. And so the coefficient of x is a, coefficient of y is b, and coefficient of z, when written that way, x plus y minus z equals 0, that's the c. So 1, 1, negative 1. And so plugging these, we get x plus y minus z plus d equal to 0 for our plane. The parallel plane is x plus y minus z equals 0 without a d, but our plane, you have to have a plus d. How do we find that? As before, plug x equals 3, y equals negative 2, and z equals 8, and solve for d, and you get d equals 2. So x plus y minus z plus 2 equals 0 is our plane. Right? Notice again, for the original plane, that z equals x plus y plane, or x plus y minus z equals 0, the d value happens to be 0. But for our plane, the d value happens to be 2. The rest is same. The x plus y minus z part is the same. So different values of d, 0 and 2, gave us two different parallel planes. That's what I alluded to in the previous slide. Cool? Okay, moving on. Find the equation of the plane. Oh, the plane through the origin and the points 3, negative 2, 1, and 1. Ooh, the plane through 3 points. Origin is 0, 0, 0. So, is there a way to finding a plane based on 3 points on the plane? How should I put it? This is actually very important because it's a very natural thing to talk about. Why is it a natural thing to talk about? When it comes to line, folks, please pay attention. When it comes to line, we always sort of think about, hey, I give you 2 points. Tell me what the equation of the line is that passes through those 2 points, we say. Right? 2 points. What's the equation of the line? Oh, and that's fairly straightforward. We use the 2-point formula. Y minus y1 is equal to y2 minus y1 over x2 minus x1 times x minus x1. Right? Basically, y minus y1 equals m times x minus x1. How do you figure out the m? M, the slope, is y2 minus y1 over x2 minus x1. Now, is there a unique plane that passes through 2 points? Is that plane unique? Answer is no. There are infinite planes that can contain 2 given points. Infinite planes. Like take your palm. That's what I'm doing right now. Take your left palm and spread your 2 fingers and touch two different parts with your spread out fingers of your right hand, your palm. Okay, both the fingertips must be touching your left palm. Now, the left palm itself represents the plane, and where your fingers are touching the palm represent 2 points on the plane. So obviously, that is one plane that is passing through these 2 points. Now, rotate your palm, keep the contact with the fingers on the palm, but rotate your palm. As you rotate, you're talking about a completely different plane. So there are infinite number of planes that contain these 2 points, right? However, the big question then becomes, Is there a unique plane that passes through 3 points? The answer is what? Is there a unique plane that passes through 3 points? The answer is yes and no. What? Yeah, check this out. You gotta be careful. Yeah, man, like if I have three different points, uh, obviously there's gotta be one single plane passing through them. Yeah, but there is a caveat. What's the caveat? What if those three stupid points lie on a single line, right? If those 3 points are collinear, that's a fancy word, basically saying they fall on the same line. Now touch three fingers to your palm, just like in the previous case, and and make sure they are all on the same line. Can you can you now rotate the palm? Yeah, you get different infinite planes. So there are infinite number of planes containing 2 points or a single line. There are infinite planes. So as long as you say that those 3 points are not on the same line, yes, now there is a unique plane. All these things you have to visualize, see, and understand. Okay? Very important concepts. All right, so let's get to seeing how do we solve this problem. What do we need in order to figure out the equation of a plane? What do we need? We need a point in the plane and a normal vector. Is there any way to obtaining do we point on the plane? Is that a problem? No, no. We have, in fact, three different points on the plane. So cool. Point on the plane is done. How about the normal vector? Check this out. Can we find a vector going from, say, origin to this point, the 3, negative 2, 1, right? Head minus tail. So that's one vector. Again, origin to this 1, 1, 1 point. That's another vector. So by doing the head minus tail to two different combinations, we get two different vectors. And those two vectors both lie on our plane because the 3 points lie on our plane. Those two vectors that we figure out lie on the plane. If you know two vectors on a plane, by taking the cross product of them, you get the normal vector. Because, pay attention, what did I say? By taking the cross product of two vectors on a plane, we get the normal vector. Why? Oh, because if the two vectors are lying on the plane, the normal vector, the cross product is guaranteed to be perpendicular to both those vectors, right? That's the property of a normal vector. A normal vector, come on, wake up, Sammy. Oh, sorry about that. The property of a cross product is that cross product of two vectors A and B is always orthogonal to both A and B. So if there are two vectors on the plane, by taking the cross product of those two vectors, the vector that we get, the cross product vector, is guaranteed to be orthogonal to both the vectors. Well, that is precisely what a normal vector is. A normal vector to a plane is perpendicular to the whole plane. That means it is perpendicular to any two vectors that you pick on the plane. Any vector on the plane, in fact. Cool? So that's going to be our strategy. Once we get the normal vector, we are pretty much done. Recall that the equation is this. Since 0, 0, substituting this, looks like I substituted this into this equation right away. We could have waited and then plugged in. Either way is fine. So when we plug x equals 0, y equals 0, z equals 0, d becomes 0. Okay, cool. We need to find the normal vector of the plane. To do this, we recognize that the normal vector must be perpendicular to any two vectors that lie on the plane, and two such vectors are P equals 1, 1, 1, and Q equals 3, negative 2, 1. What? I simply said 1, 1, 1 minus 0, 0, 0. That's how I got P. And I got the Q vector by taking 3, 3, negative 2, 1 minus 0, 0, 0. Okay. And now taking the cross product of that, we get the normal vector. Cool. Once we get that, piece of cake, 3x plus 2, a, b, c are 3, 2, negative 5. And so they plug them into that ax plus by plus cz equals 0 thing. And we got it. Cool. All right. Next. Man, this is incredibly fascinating. Check this out. Find the equation of the plane. Which plane? The plane that passes through the line of intersection of the planes x minus z equals 1 and y plus 2z equals 3 and is perpendicular to the plane x plus y minus 2z equals 1. Whoa. Our plane must pass through the line of intersection of these two planes. So if you take this plane x minus z equals 1 and y plus 1, those two planes, they intersect. The very fact that they intersect, how do they intersect? They're giving us that. They do in fact intersect. They are not skewed or anything like that. So they do intersect. And when they intersect, you have a line of intersection. Two planes, when they intersect, they do not intersect at a point. Let me repeat that. Two planes, when they intersect, they do not intersect at a single point. They intersect along a line. There's a proof for it and all that, especially when you take linear algebra, if there are any math majors, there's a wonderful proof for it. But, okay, let's move on. Okay, our plane has to pass through the line of intersection. Good. And another condition, this is a weird condition. Apparently, our plane must be perpendicular to this the third plane. Whoa, there are altogether four planes in this case. First plane is this, second plane is y plus 2z equals 3, and we need to find the intersection, line of intersection of those first two planes, and a plane passes through the line of intersection of these two guys, and in addition, our plane, the fourth plane, is perpendicular to this third plane, right? Okay, how do we solve this problem? Can we find the line of intersection? First, let's attempt to find the line of intersection. Wait a minute. Do I need to do that? I may not need to do that. Okay, let's see. Ooh, check this out. Our strategy. I got 4 points. First step, find 2 points P1, P2 on the plane by finding 2 points on the line of intersection of of the two given planes P1 and P2. Which one are P1 and P2? This P1 is x minus z equals 1 and P2 is y plus 2z equals 3. So let's find 2 points on that line of intersection. And because our plane passes through the line of intersection, the moment we find those points are guaranteed to be on our plane. What? If we find 2 points uppercase P1 and P2 on the planes P1, on the intersection of P1, P2, planes P1, P2, Because our plane passes through the line of intersection, our plane will contain those points P1 and P2. Okay, that's what I'm saying. Next, from these 2 points, find one vector V1 that lies on our plane. Right? Once you know 2 points, you can find a vector through that. From the given perpendicular plane P3, okay, find a second vector V2 on our plane. How? From P3, we can find a second vector V2 on our plane. How? Well, here is the key. If our plane is perpendicular to this third plane, the normal vector of this third plane must be parallel to our plane. Check that out. P3 is a plane, and our plane is perpendicular to this P3, but P3 has to have a normal vector which is going to be perpendicular to that P3. And because that normal vector is perpendicular to that P3, it must be parallel to our plane. The moment we have a vector v2 that is parallel to our plane, the normal vector is parallel to our plane, then that vector is actually the second vector to our plane. And use vectors v1 and v2 to find the normal to our plane. Once we know two vectors on our plane, we take the cross product of it to find the normal to our plane. So let me show you. So we have planes P1 to be x minus z equals 1 and P2 is this. And so can we find a point on this, on 2 points on this plane? How do we do that? Check this out. Suppose we set x equal, let me see, let me stay consistent. To find P1 without loss of generality, put x equal to 0 in this P1, right? And when you do, you get 0 minus z equals 1. So z is negative 1. Are you cool? So 0, x is 0 and z is negative 1. Take that z equals negative 1 and plug into this P2. So we have y plus 2 times negative 1 equals 3. So that should give us, put this in P2 to get y equals 5. Y minus 2 equals 3. So y equals 3 plus 2. And so y is 5. So that 0, 5, negative 1 is P1. Okay? All right. Next, to find P2 without loss of generality, this time you plug x equals 1. Why do you plug x equals 0 and x equals 1, man? Okay, what do you want to plug in? You want to plug 1578? Be my guest. You can plug in whatever you want. So it's entirely possible that you could try something like a negative 1 or 2 or 3, whatever for x. Once you pick an x, z is known from P1, z we find to be 0. Use that to find y from P2. So this gives us 130 for P2. And vector v1, as we said, is P1 to P2, and head minus tail gives you vector v1, which is one of the vectors on the plane. Am I boring you guys? I don't know. Okay, please bear with me. And P3 is x plus y minus 2z equals 1. Its normal vector, we know how to find a normal vector, coefficient of x, y, and z. We know that. And so V2, by virtue of being parallel to this normal vector, we can simply take v2 to be 1, 1, negative 2. Okay, all right. Mm, and like I said, once you know two vectors on our plane, let's figure out the normal vector by taking the cross product of this. And when I do, I seem to be getting negative 3, negative 3, negative 3. So that's the normal vector to our plane. What do you think about this statement? Or by scaling this, we can say n equals 1, 1, 1. Can we do that? By scaling this, we get n equals 1, 1, 1. What do we mean? What do I mean by scaling? Well, check this out. If a certain vector of some length, let's say, I don't know, a vector of length 10 inches is perpendicular to a plane, if you shrink that vector, keep the direction and everything the same, if you shrink that vector to 1 inch in length, is that still perpendicular to our plane? You bet. As long as you don't make that zero length, any magnitude of vector, once you find a vector of a certain magnitude, any scalar multiple, non-zero scalar multiple, is definitely perpendicular. Okay, so I simply chose to multiply everything by negative 1/3. If we multiply this vector by negative 1/3, which means it flips the direction and also shrinks it to 1/3 the size. And you get this one. Do you have to do this? No, you don't. It's perfectly all right if you simply say negative 3, negative 3, negative 3, and say negative 3x minus 3y minus 3z plus d equal to 0. Okay, but if you are clever and you do this, then if you plug the point, one of those points, 0, 5, negative 1, then you get d to be negative 4. Now, what did we get? We got d to be negative 4. Now, pay attention to one last thing that I want to say uh, about this one. What if we had taken our ABC to be negative 3, negative 3, negative 3? At this stage, D would we would have negative 3x minus 3y minus 3z, and D would have turned out to be plus 12. Right? Try it. If you plug this point in, you get D to be plus 12. Well, couldn't you have divided this whole equation, both sides of the equation, by a negative 3 to give us this equation? That's the idea. You can either uh, you can either stay with these values, negative 3, negative 3, negative 3, and then eventually simplify, or you can simplify in the beginning itself. All right. Um, okay. Determine whether the planes are parallel, perpendicular, or neither. Hmm. Uh, Parallel, perpendicular, or neither. And if neither, find the angle between them. Cool. Well, like I told you in the beginning, basically you do look at the normal vectors and find the angle between them. And cosine theta is n1 dot n2 over the magnitude, and went through all of this. And cosine theta, since cosine theta is not equal to 0, 1, or negative 1, the two planes are neither parallel nor perpendicular. If cosine theta is 0, that means they are perpendicular, right? Because cosine of pi half is 0. That is cosine of 90 degrees. So the two vectors are 90 degrees apart, or could be 270 degrees apart, which both would indicate perpendicular. Or if theta is 0, then cosine 0 would be 1. So that means those two vectors or along or parallel to each other. And if theta is pi, the two vectors are parallel but facing opposite directions, and we would have gotten -1. But since none of that happened, the two vectors are not parallel or perpendicular, which means the planes are not parallel or perpendicular. And we find theta to be 95.216. Just take the cosine inverse of this uh, and make sure that you pick an angle between 0 and pi. I happen to pick degrees, 0 and 180 degrees. This is pretty much the last slide, but I just want to, I went ahead and created uh, in GeoGebra for the previous problem with this long, big long problem. Can I quickly show you that, please? I'm going to go to GeoGebra and show you that. I put a good bit of time in creating that. Okay, I'll try not to take too much time. So the first thing that you see is that P1, x minus z equals 1. Okay, let me get you oriented with this one. By the way, if you download GeoGebra, you can plot these stupid equations. Okay, the first thing is um, this red always is x. Uh, I think when you initially plot this, it would look like this. And I always turn so that x is pointing towards me, positive x is pointing towards me, y is pointing this way, and z up. For some reason, I feel more comfortable that way. Okay, so this plane, the first plane, notice it doesn't have any y coordinate, right? Doesn't have any y coordinate. So that means it's going to be parallel to the green y-axis. That's what you see. So that is that x minus z equals 1. Cool. We have one plane. And the second plane intersects with this. So now I'm going to show you, display that second plane. Ta-da! That 0.5 y plus z equals 1.5. I think we said y plus 2z equals 3. For some reason, when I said y plus 2z equals 3, it said something. It had a problem with drawing that. And but apparently it's okay if we were to say 0.5 y plus z equals 1.5. I have no idea why that is. Okay, and that is this pink plane. I think I changed the colors on the planes to be able to see them well. And check this out. Do they intersect? Yeah, they intersect. Where do they intersect? That thing where the color changes from uh, pink to what is this color? Green? I'm stupid colorblind man. So where that changes, that's the line of intersection. And what I did is I actually plotted that line. Excuse me. So that's the line of intersection. Cool. Now what I'm going to do is I'll remove those two planes. I'll keep that line of intersection. Cool. And this is the third plane, x plus y minus 2z. X plus y minus 2z. Okay, it's located like that. It's not parallel to either x or y or z or anything like that, but it's certainly perpendicular to something. Okay, so that's the plane, and our plane, remember, our plane has to contain this line of intersection that, and in addition, it needs to be perpendicular to this plane. So here is our plane, and it is supposed to satisfy all the conditions. It should contain the line. So shall we focus on, let me turn the other one off. We'll just have the line and our plane. Ta-da! See that? Our plane certainly contains that line. Ain't that pretty? Okay, alright. So, our plane contains that line. Whoa, 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 what are you doing, man? Okay, now, uh, cool. Our plane contains, let me now take that line of intersection off. The only thing I need to demonstrate is our plane is perpendicular to this plane. Is that true? Do they look perpendicular? That's what I wanted to show you. Okay, so you can mess with it, manipulate it. That would be wonderful. Ladies and gentlemen,